Hi everybody, welcome back to the Feynman technique. We're going to be doing this integral that I got off of the channel Maths 505 today. It's going to be more or less the same way he solved it. There's one a little bit of a difference in the end. I think my way that I finished it off is a little bit nicer than the way he did it. But you'll see at the end. Anyway, let's just get started. We're going to create a function of t that's equal to the integral from 0 to 1 of the natural log of t plus x over t minus x all over x square root of 1 minus x squared dx. And we will note that f evaluated at 2 gives us back our original integral. Okay, now what? We need f prime of t. Well, let's just use a scratch pad over here. Let's do f prime of t is going to be equal to the integral from 0 to 1 of the partial with respect to t of that integrand. So we're going to get the integral from 0 to 1 of the partial with respect to t. Let's see, what's that going to be? We're going to get 1 over t plus x minus 1 over t minus x all over x square root of 1 minus x squared dx. And let's see, we'll cross multiply and we'll get a t minus x here, t minus x here, and a t plus x here. And we'll get, for the denominators, we'll get t squared minus x squared. So altogether, that's going to be negative 2x over t squared minus x squared. And we'll bring that down to the bottom times t squared minus x squared. All right, this x will cancel with this x, leaving us nothing but a negative 2 on top. Negative 2. All right. Let's see. Now let's okay, so let's copy this down. F prime of t is equal to the integral from 0 to 1 of negative 2 over t squared minus x squared times the square root of 1 minus x squared dx. All right. Let's make a substitution. Let's let x equal sine u. All right, so what do we get now? We'll get f prime of t is equal to the integral from 0 to pi over 2. That's how our bounds are going to change. We'll still have this negative 2. Let's see. We'll get sine squared u. No, we'll get t squared minus sine squared u times, let's see, 1 minus sine squared u is cosine squared u. Square root of that is just cosine u times dx, which is cosine u du, cosine u du. All right, that cancels and that cancels. Okay, so now we have a new expression for f prime of t. Now we have the integral going from 0 to pi over 2 of negative 2 over t squared minus sine squared u du. All right. Let's work with this a little bit more. Let's multiply the top and the bottom of this by secant squared u. And the motivation for that is because we will end up with a tangent squared u here and a secant squared u on the top. Therefore, we will have the derivative. We'll have the derivative of tangent squared u being secant squared u on the top, and that'll be good. All right, so we are, let's see, what are we doing? Yeah, we're just multiplying the top and the bottom by secant squared u right now. So f prime of t is equal to the integral from 0 to pi over 2 of negative 2 secant squared u over, let's see, this is going to give us t squared secant squared u minus tangent squared u du, right? Yeah. Yep. We don't need those parentheses. All right, and then we'll use the property that secant squared u is 1 plus tangent squared u. So I'll move this t squared over here, put a parentheses, and this will be a 1 plus tangent squared u. All right. Okay. Let's see. That's going to give us, in the denominator, we're going to have a t squared plus t squared tangent squared u minus tangent squared u. All right. Which would become a t squared plus t squared minus 1 times tangent squared u, right? Yeah. All right, let's put that in the denominator. Sorry about that puppy. He's a little whiny. So we're going to have t squared minus 1 tangent squared u plus t squared. Okay. And now we'll perform another substitution. We will let w equal tangent u, therefore dw is equal to secant squared u du. Well, there's our secant squared u du right there. That becomes a dw. dw. And this becomes a w squared. And that's it. And now you'll notice we have kind of a familiar thing. Don't forget this t squared minus 1 and this t squared. Those are just constants. So we have something in this form. We actually, oh, I'm sorry, I forgot to change the bounds of integration. If, let's see, 0, tangent 0 is 0, so w is 0. Tangent pi over 2 is infinity. All right. All right, we know that in general, under certain conditions, the integral from 0 to infinity of 1 over a x squared plus b is equal to pi over 2 times the square root of ab, as long as a times b is positive or 0. Okay. Let's see, or not 0, I'm sorry. Yeah, as long as this thing makes sense. In other words, a times b has got to be greater than 0. Okay. So what does that mean for this? This means that f prime of t should equal, let's see, pi over 2 times the square root of a, that is t squared minus 1, times t squared. Right? Wrong. Times a minus 2. So we're actually going to have minus pi over that. And then you'll notice, let's see, what can we do? We can factor out a t and get rid of this t squared. So this is what we end up with for f prime of t, and let's write that down. So now we have f prime of t is equal to negative pi over t square root of t squared minus 1. All right. But we are not interested in f prime of t. We want f of t so we can plug in 2 and get back our original integral. All right. So that means that f of t is equal to negative pi times the integral of 1 over t times the square root of t squared minus 1 dt. All right. Well, let's see. I guess we're just going to have to make another substitution. Let's let t equal tangent theta. No. We'll let t equal secant theta, I'm sorry. Therefore, dt is going to be equal to secant theta tangent theta d theta. Now let's see what that gives us. It's an indefinite integral. So, we're still going, okay, this dt is secant theta tangent theta d theta. Secant theta tangent theta d theta. This t is a secant theta, which will just cancel this secant theta. And this t is also a secant theta, but that's secant squared theta minus 1, which is tangent squared theta. Square root of that is tangent theta. So we are left with just the integral of d theta, or minus pi theta. Well, f of t is equal to minus pi theta, of course, plus c. Well, what's theta? Theta is the arc secant of t, right? Take arc secant on both sides, and we get this. All right. So f of t is equal to minus pi times, I'll write it as secant inverse t plus c. All right. Minus pi secant inverse t plus c. Yeah, that's right. All right. Oh, okay. How are we going to solve for that? How are we going to solve for that? We did not ever come up with a good value that makes this a good value for t that makes this doable. Now, what Maths 505 did is he let t go to infinity and set that equal to 0, because it would be. In other words, he got f at infinity is equal to 0, and that's legitimate, as long as you use a limit. Now, what I'm going to do is this. Let's see what happens if we evaluate f at negative 2. Well, what are we going to get in here? We're going to get natural log of negative 2 plus x over negative 2 minus x. All right. Well, let's factor out a negative sign here. And then we'll use this negative sign up here to give us a 2 plus, oh, I'm sorry. Let me do that over. If we evaluate it at negative 2, we get natural log of negative 2 plus x over negative 2 minus x. Well, we can multiply the top and the bottom by negative 1. And we have that. Well, that is exactly the negative of this. This inside the natural log, this is just the reciprocal of that. In other words, it's this to the negative 1, and we can bring that negative out. In other words, f at negative 2 is negative I. All right, and we can use that. Because that means that negative I is equal to negative pi times secant inverse of negative 2 plus c, right? Negative 2, f at negative 2, that's this right here, that's this evaluated at negative 2 is equal to negative I. All right, what is secant inverse of negative 2? That is 2 pi over 3. Secant inverse of negative 2 is 2 pi over 3. So, 2 pi over 3. All right, well, what does that mean? That means that c is equal to 2 pi squared over 3 minus I. Boy, I sure hope I did that right. Yeah. Secant inverse of negative 2 is definitely 2 pi over 3. So we get negative I is equal to negative 2 pi squared over 3 plus c, which means that c is equal to 2 pi squared over 3 minus I. All right. Two pi squared over 3 minus I. All right. Well, f at 2 is equal to I. So that means that I is equal to this thing evaluated at t is equal to 2. Minus pi times secant inverse of 2, which is pi over 3. So we'll get minus pi squared over 3, right? Yeah. Secant inverse of 2 is pi over 3. So we have minus pi squared over 3 plus 2 pi squared over 3 minus I, but I will bring that over to this side like that. All right. So minus pi squared plus 2 pi squared, that is just pi squared over 3. But that's 2I, so I is equal to pi squared over 6. And that's the answer. And I thought this was a little bit nicer than letting t go, than evaluating it at infinity. Just personal preference, but anyway, there you go. Like I said, very similar to the way he solved it, and I will link to his video in the description. So, all right, hope you enjoyed that.